Good morning, ladies and gentlemen. Thank you for coming today. We would now like to begin the Rakuten Technology Conference 2016. And let us begin with the first session titled Using Vision Sensors for Innovative HCI. Please welcome Professor Hideki Koike from School of Computing at Tokyo Institute of Technology.
Okay, good morning, everyone. My name is Hideki Koike. I'm from Tokyo Institute of Technology. So today I'd like to talk about using vision sensors for innovative HCI. And subtitle of my talk is Challenges for the Next Interactive Media. And this slide shows the outline of my talk. And first, I briefly describe what the vision-based HCI is. And after that, I'm going to talk about our work on vision-based HCI, which includes the interactive surface on the water and inspecting ball spots from ball's POV and unaware gaze navigation. And after that, I describe about the lessons learned from our prototype development. So let's go on to the first topic. It is vision-based HCI. And there have been a couple of drastic changes in HCI from CUI to GUI, and it is now moving to PUI or NUI. And first one is the character-based user interface, CUI, which use the keyboard as an input device and the character display as an output device. And after a great invention of the mouse and the bitmap display, user interfaces was changed to graphical user interfaces, GUI. And now, new HCI, which is called perceptual user interfaces or natural user interfaces, is expected. And PUI uses the perceptual technologies such as the gesture recognitions or speech recognitions as an input, and large display devices or mobile small display devices and as an output. And it is very important to notice that new HCI was always induced when new I/O devices were developed. And recently, there are great advances in computer vision. In particular, the cameras become smaller and higher resolution and less expensive. We also have open software such as OpenCV or AR Toolkit. These lead us developing vision-based HCI systems much easier. But we have been focusing on special cameras, not the normal cameras, such as infrared cameras, polarization cameras, or high-speed cameras, or action cameras, eye-tracking cameras, light field cameras, etc. And it is important that these cameras can see what human cannot. For example, a high-speed camera can capture very high-speed gestures, which human or normal cameras cannot observe. And as you know, the Microsoft Kinect projects invisible IR light, and users do not need to attach visual markers on their bodies to capture the gestures. Such invisible information enables natural and intuitive UIs. So I'd like to show some of our work which uses the special cameras and how we achieve the natural user interfaces. The first one is AQUATOP display. the interactive surface on the water. According to some reports in Japan, many people want to use their mobile devices in the bathroom. And people are bringing their own devices in the bathroom to read emails, read books, browse the internet, or watch movies. And you? Of course, yes. And however, such electronic devices are not appropriate in bathroom. Even if they are waterproofed, it is not comfortable to hold the devices on the water. But if we think about the environment in bathroom, we have a very large surface just in front of us, the water. Since we have a large surface in front of us, why not use it? So that is our initial idea. So if we project the images on the water, and we could browse internet or watch TV in bathroom. But there are lots of problems to be solved. For example, how we can diffuse the images on the water. So we developed our prototype very soon. This is an overview of our prototype. We use a projector and a depth camera, the Microsoft Kinect, on top of the water. And to make the water opaque, we put white bath salt, which is very popular in Japan. The bath salt is necessary to diffuse projector's light as well as infrared pattern from Kinect. So then we can diffuse the illuminations from the projector as well as we can detect the gestures above the water surface. So this is the very basic ideas and the prototype. And next we discussed primitive gestures on the water very carefully. Because in gesture recognition systems, it is important to make the number of gestures small and to make the gestures natural. So we discussed over and over again which kind of gestures we do in the water. So finally we decided to use these 4 gestures. One is poking the fingers, and one is stroking, and one is scooping, and one is hitting the water as primitive gestures on the water. Because you might understand that these 4 gestures are very natural. Maybe you did this in the water, right? So then poking with one finger can be used to select an object. And poking with 2 fingers is used to scaling and rotating the object. And stroking is used to swipe the display. And scooping is used to drag and drop the object. Why these 4 gestures? Let's compare with the traditional UIs. This slide shows the comparison between GUI and Touch UI, which is currently very popular, and AQUATOP display. When we see these tables, for example, the selection is currently done by touch on your smartphones or tablets. And it can be done by poking behind the water in our AQUATOP. And page scrolling, which can be done by swiping the displays on Touch UI. And it can be done by stroking the water in our AQUATOP. And the transition of the object can be done by touch and drag the icons in Touch UI. And in our AQUATOP systems, we can scoop the object and drop it to anywhere you like. And to exit the applications, maybe the home button can be used in Touch UI, and we can just hit the water in AQUATOP systems. And one another flavor we add in our AQUATOP display is a fluid simulation. Please see this video. Since we use water, we think it is more natural that virtual objects on the surface float as if it were a real object. So we integrated fluid simulation in our system. And it was very, very interesting that people felt the virtual objects float with water, although there is no relation between the virtual object and the real water. But they felt very immersive and very natural in our experiment. So this is the videos of the AQUATOP displays. Please see this video worldwide. So we put the bath salt in the water, and then we can detect the fingers and the center of palms and each hand positions. And people can select objects and drag. Even we can sync the object. This is actually not primitive gestures, but we can drag and drop. So we apply this technology not just in desktop interfaces, and we apply this to the game because people like games. And it is very easier to demonstrate our technology to ordinary people. So the system is currently detecting each fingers, and we can shoot the bullet. And this is another game implementation which was demonstrated at the Laval, France. And we didn't explain anything about this game. But by just seeing, the children can easily learn how to use this. And they do this famous gestures, Kamehameha. They even told Kamehameha when they shoot the bullet. This is another demonstration in the United States. And it was also interesting when we demonstrated these systems in SIGGRAPH. One of the major LCD company came to our booth, and they thought this was a LCD before we used this. So image was so clear and bright. And this slide shows the visibility of the images. And we can watch movies very easily, and we can see photos. And we can even read the very small text on the water surfaces. But we have to add a relatively much bath salt in the water. In current situations, maybe 20 times more than you use usually. But it could be solved. And this is, we also evaluated our pointing accuracy, the poking from the behind. And we compared with the touching. The reason why we didn't use the touch from the top is because our body will be merged inside the water when we bathe. So that's why we use the poking gestures behind the surface. Anyway, so we got many awards, including Grand Prix at Laval Virtual and Innovative Technologies Award from METI. And personally, I liked the Toretama Award from TV Tokyo. Anyway. Okay. The next, I'd like to talk about our BALLCAM systems, which we are currently working very hard to develop. And one of the most important and promising contents of the future in TV or interactive media is sports. And I will describe our approach for spectating ball sports from ball's point of view. Sports broadcasting is usually done by using multiple cameras deployed outside of the play field, or maybe we could use the handy cams or crane cameras. And it is difficult to provide the view from the inside of the play field. This is because the camera might interfere with the games and would be dangerous for the players. On the other hand, cameras are becoming smaller and smaller and lighter, as I told you before. So if we put the cameras in the ball, we could get ball's POV, point of view. And this is our initial idea. And we developed our first prototype very soon, called the eyeball, which has 6 iPod Touch in the ball to confirm our concept. The reason I developed this prototype is when I talked my idea to my students, nobody understood that, to embed the cameras inside the ball. So I developed this prototype using the iPod Touch and then showed how it can be used to broadcast the images, or even if we can display something inside the ball, if we have a display on the ball or in the ball. So this is a kind of joke, but we put human's head inside the ball. So you can see person's head from any directions. But after prototyping, but before prototyping, we already knew what is difficult. The most difficult problem is the ball is spinning very fast. For example, in our examples, I will show you later, it rotates over 600 RPM. So how to stabilize this video is a very important issue to establish these ball camera systems. So this is the raw video from one GoPro in the American football. So we put one GoPro inside American football because the spherical camera is much more difficult to do the stabilizations. So we first focused on the American footballs. And please see these raw videos. So this video was taken from the GoPro inside the ball. So this is a raw video. So we didn't get any meaningful informations from the video. So maybe most of the people will give up at here. But we didn't. So I thought that if we use advanced vision technology, we could provide the virtual views as if the ball is not spinning. So this is an overview of our algorithm. Since we do not have enough time to describe this in detail, I'm just going to show an overview of our algorithms. The first, we correct the lens distortions and rolling shutter issues, which often sees in CMOS cameras, simultaneously. If we do not correct this lens distortion issues and the rolling shutter issues, the images from the camera is distorted like the left photos on this slide. It is very hard to detect the feature point. So we first correct the distortions. And then, next we select images seeing downwards by using the intensity of the images. Here we have some hypotheses. For example, the axis of the rotation of the ball is always the perpendicular to the ground, as you can see on the top left of the slide. So the ball is rotating and captures images, the top and bottom and top and bottom. So when we see the intensity of these images, you can see the top right of this slide that it has some cyclic intensities, bright and dark and bright and dark. So if we put some threshold in here, we could correct the images which sees downwards. The bottom photos on this slide shows the result of our image collections, image selections. But each image is not large enough to do the feature matching. So we extended the views by using multiple frames. For example, if we have 3 frames, we could get the triplet images, which is shown on the center of the slides. And then we could get another triplet images. And we combined those triplet images and we provided the 6-let images to extend the views. So after this, we did the image interpolation, interpolating the images. Because the ball is spinning and we take the pictures when the ball is seeing downwards, the image sequence is relatively not continuous. So we have to do the image interpolations. So, okay, let's see the result videos. This is the input sequences which I showed you before. And this is the result. The left hand is the original video, and the right hand is a proposed approach. It is too fast still. I'm going to show you the slow motions. So as you can see here, in our proposed approach, the ball seems like it's not spinning. So we are developing this technology to enhance our algorithms right now. And also, this was applied to the American football. But currently, we also developed another technologies for spherical balls. I'm going to show you the videos. So imagine we are doing the bowling like this. Did you understand? The ball hit the pins. But we can correct the images like this, the movies. And this is another scenario. We are passing the balls. The ball is spinning. But if you see the right-hand videos, the ball's POV is always fixing to some points. I'm going to show it again. This is a bowling scenario. So ball is spinning. But we could fix the ball's point of view like this. So we have been making many ball cameras as shown in the slide from 2011 to now. And our main goal is our ball is used in the Rugby World Cup in Japan, which was held in 2019, and also in the Tokyo Olympic Games 2020. But it might be rather difficult. But maybe our ball can be used in some kind of exhibition matches or demonstrations. And as you can see here, the ball is not the plot type right now. If you see the American football on the right top of the slides, it looks like the real American football, but we have a very small cameras inside. So we are looking for the researchers or companies who collaborate with us to make these ball systems. And we are very happy to collaborate with the peoples. Okay, next. I'd like to talk about unaware gaze navigations, which is also a recent research results. Here is an example of the web pages of electronic market. And if you want to guide users' gaze to any particular advertisement or any particular items, how do you do it? Flashing the object? Or vibrating the object? Changing the colors? Or appearing some avatars to show these items? But such visual effects might be uncomfortable to users. In my personal opinion, such visual effects is not good and is not popular to the customers. This is my personal opinion. So we want to navigate users' attention more naturally and even unconsciously. So first, please see this slide. I think your gaze moved from the wave to Mount Fuji. Do you want to see it again? This is the first slice. Then maybe your gaze moves to Mount Fuji. This technique is very popular in TV programs or movies. In this case, you easily recognize the blur of the images. So then your eyes, your gaze, move to the object which is not blurred. However, our focus is on if we can navigate your gaze without being recognize this blur. So we did some experiments. So here is the sample, the snapshot of the experiments. So we put the gaze trackers under the PC's display and show some images to the subject. And the subject is seeing the images, many images. And we asked subject to see images without saying anything about blur. We just told them to browse the image freely. And we recorded users' gaze by using gaze trackers. And this slide shows the result of the experiment. An image on top left is an original image. An image on bottom left shows at which point users saw by using heat maps. On the other hand, an image on top right is a blurred image, slightly blurred image. But a small region remains unblurred. In this slide, the small white circle is on left-hand side of the image. You notice? That is the regions which are not blurred. And the image on bottom right shows at which point users saw. As you can see, the user's gaze was statistically guided to the unblurred regions. So this is the similar result when I show you the Hawk size, the image. But we did the same experiment by using many images, and this slide shows the different images and their heat maps. In this case as well, the user's gaze is statistically moved to the regions which is not blurred. And this graph shows a relation between the blur strength and the time until subject's gaze enter to the unblurred region. And the horizontal axis shows the blur strength, and the vertical axis shows the time for fixation. And this is there is a significant difference between sigma equal 1 and sigma equal 2. I don't talk about the detail in the I do not talk about the detail of the blur strength, but we use a Gaussian blur in this case. But just please remember the blur strength sigma. If the sigma becomes 2, your gaze moves to the unblurred region. And then we conducted another experiment. We asked the subjects to see the images. And this time, we taught the subjects that the image would be blurred gradually. So if you realized the blur, please click the mouse button as soon as you can. So this is what we told the subjects. And this graph shows the relation between the time to be completely blurred to the sigma equals 5 and the blur strength when the subjects click the mouse button. For example, when it took 15 seconds, please see the 15 on the horizontal axis. When it took 15 seconds from sigma equals 0, which means unblurred, to 5, the maximum blur, the subjects click the mouse button when sigma equals 2.3 in average. And if you see the blur, if you see the horizontal axis of the 3, it's going to take about maybe 3.7 or 8 in average. Blue dot indicates the average value, and the blue dotted line is a simple fitted line. And it is, however, reported that it takes 300 milliseconds to click the mouse after the user recognizes the stimuli. So the red dotted line is a fitted line when such latency is taken into account. From this graph, it is seen that average sigma values are always more than 2. So please remember that user's gaze moved when sigma equals 2 in experiment 1. However, users recognize the blur when sigma is larger than 2. It indicates that if we blur the image between 2 and 2.3, maybe, users' gaze statistically moved even though they do not realize the blur. This is very interesting results of our experiments. We didn't expect. So how can we use this result to any scenarios? Here is a scenario when method is used in electronic market. When the user is browsing the market, the resolution of all items but today's campaign item would be decreased below the threshold at which the user can recognize the modification. Statistically, this item would have more chance of selling. This is our scenario. And some people might wonder, this might be any control, unrecognized control of the blur might be not good. But in my personal opinion, it would be okay because we didn't hide anything. And the user can show anything you want, but we just slightly blurred the images. Okay, finally, I'd like to talk about lessons learned from our prototype development. This slide shows an example process of how ideas become to a unique one. The first, you might think that you have a new idea. However, in most cases, it is not at all. So please survey the other work very carefully and very widely. There is very similar work all over the world. And after that, okay, it seems that your idea is new. However, the world population is over 7 billion. So maybe 10,000 people in the world might be inspiring the same idea at this same moment. This is kind of a joke, but there are lots of people who think similarly. So we have to make the prototype as soon as possible. So it is very important to make prototype because you know the idea is not so interesting as you thought by making the prototype. Or the idea is more interesting than you thought by making the prototype. So it is very important to make the first prototype. And okay, it seems your idea is interesting. In this stage, the 99% of people who had the same or similar idea did nothing. They just think. They didn't develop the prototype. So you might be a 1% who had that good idea. But still, 100 people are making the same prototype at this moment in the world. So let's do the serious implementations from now. So it requires various skills and knowledge. And however, you may face very difficult technical issues, maybe, always. And most of the people gave up this idea in this stage, even if they make the prototype, because they cannot solve these technical issues. But there were many geniuses in our history, so we should learn from them. In our prototypes, we always find the solutions from our predecessors' knowledge. So if you find the solution for the issue, you may be the only one who finally developed the systems. Okay, here is the conclusion of my talk. And thank you very much for your attention. And I'm happy to answer your questions. Thank you.
Thank you very much, Professor Koike. And now we will take a 15-minute break. The next session, titled Experiences with PlayStation VR, led by Mr. Yasuo Takahashi, Director of Hardware Global Product Strategy and Management Department, Sony Interactive Entertainment, will begin at 12 o'clock. So please come back by then.